As mentioned before, the fundamental principle of operation of an optical puff relies on the high physical complexity of optical scattering by a unique semi-transparent medium. Based on the design guidelines extracted in the context of Work Package 5, and in particular in the deliverable 5.3, an alternative puff configuration is proposed, based on an optical waveguide. Aiming to validate the predicted performance enhancement, we have generated various in-lab prototypes. Here we present the latest version. In detail, the puff score is incorporated in the plastic case and consists of an infrared diode laser that illuminates a spatial light modulator that follows. The spatial light modulator has 1080p resolution, and by switching on and off discrete pixels, we can change the spatial profile of light reaching the puff specimen. Through this mechanism, we can generate exponentially large pool of inputs, as described in Work Package 6 and 5. The puff specimen is a large-core, low-cost, commercially available polymer optical fiber, 3 cm long, with 980 micrometers core and 20 micrometers cladding, and it's fully described also in the deliverable 5.3. The puff's facets are processed through a noise-driven friction system, aiming to insert random defects, while the generated unique speckle patterns emitted by the puff's output are projected to the camera attached to the system. In this case, this is a 5 megapixel camera. Besides puff score, we have used a system on chip that provides a threefold operation. Firstly, the system provides all the control and monitoring signals for the different electro-optic modules of the puff. In detail, it regulates the current and temperature of the laser. It drives the spatial light modulator through a VGA interface, thus enables channel generation, which is a critical part for random number generation. It also captures the speckle images from the camera module. The second fundamental operation includes the processing of puff's raw responses, the speckle patterns. Aiming to generate an autonomous system, a dedicated ARM processor hashes the images through different mathematical processing techniques and produces random binary strings of any length. Finally, the last operation of the system on chip is to provide a secure network interface to the other modules of the Konfido architecture and provide cryptographically compatible random numbers.
In order to demonstrate our prototype's capabilities in action, we will present a typical operation scenario. This scenario involves a PUF administrator that sets up and initializes the PUF hardware modules and the network interface, and a PUF user, where in our case it can be another Konfido module, for example the SGX enclave. In the first case, the PUF's administrator is remotely connected to the PUF hardware module. The first action consists of initializing the laser module. Typical parameters include current and temperature. PUF's control sends monitoring signals like the output power of the laser, the voltage of the diode, and the recorded temperature for control reasons. The second action consists of setting the spatial light modulator's resolution. The administrator can regulate camera's resolution and other parameters like the exposure time, and can enable or disable averaging. So as to demonstrate these basic operations, we can change the spatial pattern pixels applied to the spatial light modulator, and we record the variation in the generated speckles. These variations in the raw images recorded can be exploited so as to generate random numbers. It can be noted that for monitoring reasons, we also compute the intensity distribution for all colors, red, green, and blue. It is also worth mentioning that for all colors, distribution follows a typical gamma function, as dictated by the theoretical analysis presented in the deliverable 5.3. For simplicity's reasons, we can record only one color. In this case, red, which matches with the laser's emission wavelength. The PUF system on chip not only records the raw images, but also can use different hashing techniques, for example the random binary hashing technique, so as to generate random binary strings. So as to visualize this operation, we now record the processed image alongside the intense distribution, which now is uniform. For each spatial light modulator pattern, we demonstrate the processed image after hashing alongside the generated binary string. If we change the pixels, then the image changes, and so the 64-bit random number presented in hexadecimal form changes as well. These basic operations are included in a server application that is executed in the PUF system on chip. This application provides the required operation defined in work package 6 and work package 5. It generates on demand random bit strings directly from the PUF system. The client application, on the other hand, is executed in a trusted execution environment and creates a secure connection with the server. It requests for random bit strings of particular length. The server sends the data over a secure connection. It is worth mentioning that the generated bit strings are checked through typical tests like NIST, die-hard and die-harder, CTW and other, so they are cryptographically compatible. In order to summarize, in full accordance with Konfido's description of work, we demonstrated a novel photonic PUF module that demonstrates enhanced resilience to cloning compared to the state of the art, able to be connected with the other Konfido's federated modules, and provide random bit strings on demand.